Hello everyone, today I want to talk about uniform circular motion. So in one of the previous videos where I took the derivative of position with respect to time, which I actually want to do again really fast here. So if we call this our position vector at time 1 and that our position vector at time 2, then we could say that this infinitesimally small change in position, dr, would be parallel. So everything's parallel there. Whereas now, I want to talk about what if dr is perpendicular to the position vector. Okay? So here, I'm going to draw our initial position vector again. But this time, what if R2 is inclined almost at some angle, theta? Well, then what we find is that dr, this really small change in r, is actually perpendicular to r. Okay? So just to show you what that might look like really fast, I'm just going to use the marker as a vector again. And I think it's best for you to see this instead of having me draw it out. But you can see that over time, if we keep having a perpendicular change in r, just the direction is changing. I can't change the length of this marker at all. But by adding perpendicular displacement to it, I can change the direction in which it's pointing. You could think almost of propping something up with a wedge and how it would go from perfectly parallel to a surface to being inclined at some angle. Okay. So really quickly, we need some way to describe this angle. Well, I already called this angle theta, as you can see right there, but I want to specifically talk a lot more about what theta's derivative would be. Since, we're taking the derivative of everything else, so why not theta, right? Well, we actually have a name for this, and it's called angular velocity. Okay, so that dot, if you remember, just means time derivative. That's Newton's notation. I really prefer to not use this notation and just to use the Greek letter omega. It looks like a W, but it's omega. Okay. So next up, what I want to do is I want to give you a formula for how some angle theta would change. And not like taking the derivative of it, finding angular velocity, but we specifically want to know an equation to find theta. Okay? So I'm going to write this in a little bit more of a conventional format. We can say that the derivative of theta with respect to time, d theta dt, equals omega, angular velocity. Okay? Next up, multiply either side by dt, and we find that this very small change in theta equals omega times this very small change in time, dt. Okay? Now we can take an integral here, and an integration is like taking a continuous sum, which just means you're summing over like an infinite number of points, so to speak. So this infinitely small angle summed over however many points, we can just call that a large angle, or at least large comparatively. They could still be very small, like 1 degree, but that's large compared to this very small change. And we get that theta equals omega t, and our constant of integration is going, I like to call it theta naught, because it just is the initial angle. Some books that I've seen will occasionally use the Greek letter B, which looks like that. It kind of looks like an empty set, if you know what that is. But sometimes books will use that. I think it's just so much clearer to use this because you're not showing them some random separate angle you're bringing into the equation. It's just theta, but at the initial time t. Okay, so if we want to talk about uniform circular motion really quickly, there's one more equation I want to talk about. And it's that the velocity vector in uniform circular motion is usually equal to r, which you'll see what r is in a second, times our angular velocity, which is the Greek letter omega. Okay, so now I'm going to very, very quickly and very poorly probably draw a circle. Okay. Not horrible, but certainly not great. Okay, so the circle has the radius of r. And that's what r is here. It's the radius of our circle that we're making. What I want you to think about whenever you hear uniform circular motion is just a particle going around and around and around and around and around and around and around this circle. Okay? So we can say, I'm going to say that our particle, the initial position, which I'll call r naught, is going to make an angle of 0 degrees with the x-axis. Okay? And the reason I'm doing this is just to take a constant out of integration, basically. But at time, we'll say t equals 1, so I'll call this r1. Make it a position vector. We're going to have an angle, some angle, we'll call theta, okay? And now if we want to derive an equation for theta, we can do the same thing we did before, except we won't need theta naught, because theta naught's just 0. So you could do the same thing, you could just memorize it. I always recommend you know how things are derived, but there are some things in physics you just do so much, like you're going to memorize it. So we could say theta equals omega t. Okay? And really quickly, I want to go back to this velocity vector. So I already talked about the change in position, which if we know there's a change in position, there is a velocity. If there's a change in the position's direction, or if there's a change in the position's magnitude, there is a velocity. We can tell that r is changing here. But the magnitude of r isn't, because a radius of a circle, which is essentially what our position vector is, should be constant at every point in the circle. So, and this is not a perfect circle, which is why it's not. But if we're assuming this is a perfect circle, r has the same value, magnitude, that is, at every point, but its direction changes. So we can already predict that this velocity is going to be perpendicular to our position vector r at any given time. As we get into more complex examples, sometimes our position vector will kind of jut out and increase in magnitude. But really we need a different coordinate system to describe that, which is what I'm going to get into next video. So we have a velocity vector that's always perpendicular and we can say that's tangential in this case. So I'm actually going to grab my protractor really quick just to try to make this at a right angle tangential to the circle. There we go. Best I could. Tangential to the circle, right angle with R. Okay. So, you might be thinking, well, okay, so if we have a velocity vector here, what's the difference really between velocity and angular velocity? I get that velocity is the change in position, but the change in position has to do with the angle theta. So if you're looking for a more specific definition, I think I might be able to help you here. So velocity, as you can see, even by this formula, is measured in meters per second. Okay, angular velocity, which is this, omega, well, omega is measured in radians per second. Okay? And radians don't have a unit. Radians are unitless. But the reason we're going to use radians here as an alternative way of measuring angle is because radians are natural for circles. They are. They're much more natural than angles, like in degrees. So we are going to use radians in this case. I hope that you're familiar with them. If not, I really do recommend you get familiar with them. And I know I did use degrees there. That's kind of my own fault. But 0 radians is 0 degrees, so it doesn't really matter. So, I want to do an example really quick, because this can get kind of confusing. But before I do that example, I want to quickly note that if our velocities in this direction are angular velocity, which is the rate at which our angle theta changes, would be going this way. Okay. All right. So really quickly, I want to talk about an example of this. I think we all know an analog clock. So, I know they might seem ancient today. They're not really, but, I think a lot of the younger generation tends to think that way. But I think that can kind of help us with physics and understanding uniform circular motion. So, really quickly, I'm just going to quickly draw in a clock, okay? I'm actually going to give it 2 circles here, so to speak. This is like the outer layer of the clock. And this is just going to be the trajectory of our second hand. I am going to look at the second hand because, to be honest, the minute and hour hand move really slowly. There are certain clocks where the second hand will move constantly, and it won't just like tick, 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 but it'll actually just move fluidly like that. And I'm going to be assuming that this clock is like that, just to keep things simple. Okay? So at time t equals 0, I'm going to draw our little origin in there. The second hand is going to be right at the 12. Okay? And we're going to have to use angles from this 12. Don't try to do it from the x-axis. Just do it from the y. Because this is where we are at t equals t naught, or t equals 0, in other words. Okay? So now, our second hand has moved and over some time. Now our second hand's here. It's probably about halfway between 1 and 2-ish. Maybe actually it might be right on 2. Doesn't really matter. Anyway, we'll say here's our angle, theta. This is the second hand at t equals 1. Okay? And now I want to try to describe this thing's motion. Well, we're going to need one more value here, and that's going to be L. And I'll write L in cursive just so it doesn't look like a 1 or something like that. Kind of like how I do my T's, like that, so they don't look like a plus sign. Okay? I will learn to stop hitting the camera one day. I really swear I will. So length measurements can actually be very useful. And I think even going into the next chapter, we will find that out even more so with pulleys. But we can say that our length here, L, is a really good measurement to have because we can kind of describe the motion with it. A big difference between velocity and angular velocity is how fast they are, so to speak. So velocity depends on your position from the origin, right? R. So if you just turned at the origin at an angular velocity, and you could just imagine yourself standing there turning back and forth, you could go at some angular velocity. That's pretty quickly. But if you went out further from this origin and you tried to go at the same angular velocity, you'd have to be like full on sprinting in a circle, and it would be so much harder to keep up with somebody who's just spinning in the center. So we can say really that oftentimes our velocity vector is much, much larger than our angular velocity. A little bit of a tangent, but I do really hope that helps you understand it a little bit better. And just to define our coordinate system here, I do want to add in our unit vectors, x hat and y hat. Okay? And a clock really is pretty much two-dimensional. We can treat it as though it's two-dimensional. That's a good assumption to make in many cases, but it's just not in others. Okay? So I want to describe this thing's position as a function of time. Well, I'm going to kind of make it a little bit larger over here, specifically just the second hand. So if this is our second hand kind of magnified a couple times, like there's like the outer trajectory of it there, we got length L, okay? And here I'm going to define this right here. That's the angle theta. Well, this is actually going to become very important because we can kind of just make a right triangle right over here, okay? Now, right here we can say that the sine of our angle theta equals the opposite over the hypotenuse. Okay, so opposite in this case is going to be right over here in the x direction, so that's going to be our length in the x. I'll just denote that with Lx over the hypotenuse, L. And the cosine theta is the adjacent side over the hypotenuse. Adjacent's right here. That's going to be our y. So our length in the y, so to speak, over L, which is our hypotenuse. Okay, and if you rearrange this, and you'll honestly probably memorize this rearrangement because you'll have to do it like 50 times in one problem. Exaggeration, but I hope I proved my point. So really what we can say here is that our length in the x direction is going to be equal to L sine theta, and our length in the y direction is going to be equal to L cosine theta. Now, I forgot to add this here, but we are going to move with a constant angular velocity, which honestly I shouldn't really have to add that there because a clock, it has like a set, distance it's going to move. It's not going to like experience something called an angular acceleration, which I think you can guess is just the change in angular velocity. And instantaneous angular acceleration would be the derivative of angular velocity with respect to time. I think you can probably guess that there's going to be no angular acceleration because the second hand doesn't like speed up, because then that would throw time out the window basically. We'd have no really good way of measuring time. So obviously it's going to have a constant angular velocity, omega. Okay? So here we can call this 0 degrees and then just perfectly measure from here. So we are just going to say that theta naught equals 0 radians. I'm not going to use degrees. I know I said degrees, but I'm not going to use that because it's an angle. It's uniform circular motion. Angles in uniform circular motion are best described with radians. Okay? So now if we want to write our position as a function of time, okay, we are going to say that, well, if, considering we're saying that our initial angle equals 0, just to rewrite this, our angle theta equals omega times time, angular velocity times time. And we can say that, well, it's going to be in the x direction. We already have it right here. It's going to be L sine, but instead of writing theta, we're going to write omega t to show that it changes in time. Put our x hat, and now plus L cosine omega t and the y hat, and I do realize I kind of ran into myself there, so I'm just going to draw a little bit of a line. Okay. Now, if we want to find our velocity as a function of time, well, you might instantly think to try to find an actual value for velocity, and if you wanted to do that, you would use this formula, but we really just want to find it as a function of time. In other words, how it's changing. Specifically, more in direction than magnitude, because magnitude will be constant. So, because again, there's no real angular acceleration. So, here, we can just take the derivative of this. Okay, so really quickly, I'm just going to give you a little bit of a rule with derivatives here. So, the derivative of the sine of some constant times x, well, this will be equal to the constant times the cosine of the constant times x. In other words, the derivative with respect to x of the sine of kx equals k times the cosine of kx. And then the derivative with respect to x of the cosine of kx is just going to be equal to negative of the constant times the sine of kx. Okay, so cosine goes to negative sine, and we take the constant out. Sine goes to positive cosine, take the constant out. All right. Now, we can go ahead and find our velocity as a function of time. So omega is our constant here. T is obviously going to change. So I'm going to go ahead and take omega out. Rewrite L, since that's just a constant. Won't even have to do a power rule or anything like that because it's a constant. Though I guess you could do the power rule if you really wanted to, but it'd just be 0 times the derivative of this, or 0 times this, which is just 0. So you could do the power rule if you know what that is, but you don't have to here. So, or the chain rule, I guess, if you really wanted to get fancy with it. So take out omega, have L here. Now we're going to change the sine to a cosine and leave the inside as omega t. And this will be the velocity in the x-hat direction. Plus omega L. Or sorry, not plus. Minus omega L times the sine of omega t in the y-hat direction. Okay, and I'll put parentheses just to make what's in and out of the sine function a little bit more clear. Sorry if that wasn't clear. Okay, and now we're just going to basically do the same thing again to find acceleration as a function of time. I think my cat is upset. If you heard that, I don't know if that's audible or not, but that's kind of funny. So take omega out. We get omega squared because we have 2 omegas times L, length, negative sign, because it is the derivative of a cosine function. So the sign switch, we get the sine of omega t in the x hat. We're going to keep the minus sign here because sine is positive, the derivative of sine rather, is going to be positive, but we already have a negative outside. Negative times positive is just a negative. You get the same thing on the outside, but now it'll be a cosine function, and that's going to be in the y hat direction. Okay? And that's what we'll find. And as you can see, this is a very, very lengthy process. Even for something as simple as a clock, we haven't even gotten to where the radius of the circle is not constant and will be getting bigger and bigger each time. In other words, the second hand would like jut outward in the middle of moving. We haven't even gotten to that yet, and we can already see that this is pretty lengthy. So you might be thinking, there's got to be a better way to do it. And in the next video, I will talk about the better way to do it. As a last really fast note here, just as a little bit more of a conceptual view of this, the sine function and the cosine function, if you graph them out, they look something like this. And it'll depend on what the situation is, what's being done to it. But it'll look like a wave, basically, like up and down and up and down. If you've already had like a small introduction course on physics, like in high school, we'd call that a transverse wave, and it looks like that. But basically, what is this saying is that the graph of the motion is going to repeat. So you can think of the second hand on the clock as a wave. Its position gets higher in time, and then lower, and higher and lower and higher and lower, and as it just keeps going around the clock until the batteries run out, probably. But we could say for infinitely if we had infinite batteries. Okay, that is going to be it for this video. If you liked it, leave a like, maybe subscribe. I hope you have a great day, night, afternoon, whatever, wherever you are in the world, whenever you're seeing this. See ya.